Hi, we're Team Animorphemes and this is a question answering system. The logic for the asking system is this. We first extract candidate sentences that match the pattern that we define and truncate it into a simpler sentence, and then mark the movable phrases at the same time. We then choose the answer phrase and generate possible question phrases for WH questions. Next, we decompose the main verb if it is not auxiliary, and then invert the subject and the auxiliary. For WH questions, we insert the question phrase in the next step, and then we need to perform some post-processing to generate our final question. For example, if our sentence is, in 2008, because of the Olympics is coming, 5 valuable pandas including Jing Jing were born in Beijing, China, we reformat it into two simple sentences. Olympics is coming and in 2008, 5 valuable pandas including Jing Jing were born in Beijing, China. The movable phrases NP, VP and PP are marked at this step. Then for yes and no questions, we check if the simple sentence has an auxiliary. If not, we decompose the verb first. Then we invert the subject and the auxiliary or the verb. For no questions, we replace the subject with other noun phrases that appear in the article, such as swallows in this question. For WH questions, we will identify if there is any named entity in the movable phrase that can serve as the answer phrase and then map the named entity with the question phrase. For example, if the named entity is the location, then the question phrase would be where. If the named entity is time or date, then the question phrase would be when. If there is no named entity, then the question phrase would be what. The answer phrase can be selected from PP, NP, or VP. Based on the origin of the answer phrase, we apply different strategies to form our question. We invert the subject and auxiliary or verb and insert the question phrases for WH questions. Additional post-processing is required to ensure proper formatting and punctuation, like capitalizing the first letter and changing the periods into question marks. Our question evaluation system considers 4 factors, including complexity, difficulty, diversity, and fluency. For evaluating the complexity of the question, we use buckets to represent the different scores. These indicate the number of words in the question. If the question is in the 520 bucket, then it achieves the highest score. If the number of words is smaller than 5 or greater than 30, then it gets the lowest score. The position of the question word or WH word indicates difficulty score for the question. The grammar checker is used when there are not too many candidate questions, since it takes time for us to get a response back from the Ginger server. To guarantee the diversity of the selected questions, each type of question is assigned a percentage. Finally, our answering system consists of 3 components. The answer type detection component will detect the type of the answer to the question. The passage retrieval component serves as a search engine to retrieve those most related sentences in a document. And then the answer extraction part takes the outputs from the former 2 components to extract and construct a sentence to the question. The question classifier extracts the answer type of the question, which will serve as input for the passage retrieval and answer extractor components. The training set and the test set come from Lee and Rod's datasets. The features include syntactic features such as part-of-speech tags and semantic features like named entities. They all come from a bag of words. The algorithm we use here is a support vector machine, and we finally achieved an accuracy of 81.8%. Further, to enable the answer extractor to use the answer type, the result is mapped onto the 17 typed of named entities in the spaCy package. The passage retrieval component can find the best matched sentences using the given document and a query. We use the entry model for a retrieval model. This is an inference network model with smoothing parameters, so we can always get a score for each sentence even if it doesn't contain a query term. It works better both in precision and recall than the basic TF-IDF model. During the information retrieval, we remove the stop words from the query and then stem it using the Porter stemmer. Our article is also stemmed, but the stop words are left intact, and then we index each sentence in the article and build an inverted list for each term. We then compute the entry score for each sentence and rank these sentences based on this score. We finally return the sentence which has the highest entry score. We tested the accuracy of our passage retrieval model based on our asking program. On the questions generated by our asking program, our accuracy is 93%. For the top 100 questions that have the highest quality, we achieved 95% accuracy. After getting the original sentence in the article that contains the answer, we post-process the sentence to extract the final answer that is as concise as possible. For WH questions, we first try to locate the answer using named entities. But our implementation detail is different for where, when, and who. We developed a heuristic approach for answering yes or no questions. The basic idea is this: if all the nouns in the question can be found in the retrieved sentence, then we answer yes, otherwise no. For other questions, such as what, why, or how, we simply return the passage. For who questions, Spacey sometimes gets confused between person tags and organization tags, especially for strange person names that it hasn't encountered before. For where, multiple locations can occur in one sentence, and sometimes the location cannot be recognized by the NER tagger. For the when question, the NER tagger is relatively more accurate. Thus, our strategy is this: if we find the required NER phrase in the sentence and this NER phrase is not in our question, we return the NER phrase. If no name is found, then we return the original sentence. The reason that we use noun phrase matching instead of verb phrase or noun phrase structure is that after lemmatization, noun phrases have less variation compared to verbs. The only tricky part is matching the person name. A question may contain a full person name, whereas a retrieved sentence only contains the first name or the last name. We allow for partial matching in person names. For noun phrase matching, we use lemmatized words. For name matching, it is case sensitive and we try to return exact matches. For sentences that do not contain any noun, including the name, our heuristic strategy fails, and in this case, we just return the original sentence. Since this is a video, you won't be able to ask us any questions, but as we've just shown you, we can ask and answer many of yours. Thank you.